So in the last lecture, we were discussing that this diameter seems to be the diameter from the center of cylindrical wall to the center of cylindrical wall on the other side of the cross section. But if you look at the whole cylindrical shape, you can see that the fluid will move inside this cylinder from this direction, let's suppose. So when we have to calculate this bursting force is acting on the inner wall or on the inner side of the cylinder. So it has nothing to do with the thickness. For example, from this shape, you also see that this bursting force is acting on the inner side of this cylinder. So that is why this diameter is the internal diameter. But again, this diameter may seem to be the diameter from the center of the wall thickness to the center of other wall thickness. But just for the sake of simplicity, so that we can have a simple expression to calculate the loop stresses, it has been assumed that this diameter is also the internal diameter, and so we got the final form of the equation like this one. So in yesterday we concluded that this diameter is from the center, so just make that correction that this is the internal diameter. So whenever in the numerical question you get this diameter, you have to substitute the internal diameter of the cylinder. And even if you substitute this diameter from the center of this wall thickness to the center of the wall thickness on the other end, the difference between the pressure is just very small. It would be something like maybe if you substitute the value as, let's say, 100 for this diameter, that is the internal diameter, and you calculate this longitudinal length, you may get answer like something 9,000 psi. Okay, but if you substitute this half thickness on either side, that you may get the answer something like 9,020 psi. So there won't be much difference in the value of the stresses if even if you substitute the thickness of this. But for the sake of convenience, this you should always use the internal diameter. So just make this correction. And same is the case for the hoop stresses, that in this equation, this diameter is the internal diameter. So the next topic was what is the effect of end plates and joints. You might have observed that in the case of cylinders, there are different sheets are sometimes connected with the help of these kind of joints, which are called as longitudinal joints, and also there are these joints that are called as grid joints. Now, obviously, when you provide these kind of the joints in any type of the structure, you have to make small holes to insert the bolts or any kind of a connection over there. So due to those holes, the cross section of the section or the plate would reduce, and it will cause the reduction in the strength. Now, it will cause the reduction, and what will happen that when the fluid is flowing inside the cylinder, more stresses will be produced or will act on the cylinder, and the chance of failure of the cylindrical shape will be more. So actually, you might have observed that in the case of cylindrical sections, there are different plates which are molded in which are connected with each other to make a cylindrical shape using some kind of joints. So when you provide the joints in the cylinder, you have to make small holes in the plate to insert the bolts or the joint. So what will happen? When you insert the hole, the cross section or the area of the sheet will reduce. For example, let's say if this is the straight sheet and you make the holes over here to insert the bolts on any other thing, then the cross section area will reduce. So when the cross section area will reduce, the stress is force over area. So the stress will increase. So what will happen if the stresses are increased? So stress is due to the fluid flowing inside the cylinder. The stress will increase, and the chance of failure for this cylinder will increase. So that means the strength will reduce. Stress will increase, but the strength of this cylindrical section will reduce. So for different type of joints, there are two factors. For the longitudinal joints, the factor is efficiency of longitudinal joint, which basically for different types of joint, it is specified by the manufacturer that how much strength will be reduced when you install this type of a joint. So we will be provided with this factor NL or NC, and this can obviously we know that it will cause the increase in the stress. So for the longitudinal joint, you can see that these are joints which are in the length. It will cause the increase in the stress or increase in the hoop stress. So that is why this factor will be divided in this equation just to cause the increase in the stress. So this was our original relationship when there is no joint in the cylindrical shape. So when there are joints provided in the cylindrical shape, we have to increase this stress. This stress won't be this one. So by which factor this strength will increase? It will increase by this factor NL in the longitudinal direction, because hoop stresses are causing the hoop stresses are, for example, in this figure, we see that we cut the section, or we cut the longitudinal section, and in the longitudinal section, hoop stresses are provided. So the joints in the longitudinal direction will cause the increase in the hoop stress. And similarly, this factor NC is the efficiency of the circumferential joint, and the joints in the circumference will cause the increase in the longitudinal strength. So these factors depend on the different type of joint, and it will be specified by the manufacturer always. So is there any question about this one? If not, we can solve one simple example problem to understand the application of the different formulas or different stresses that we have just discussed. There is a cylindrical portion which contains a gas, let's say a propane tank, which has an outer diameter of 12 inches and wall thickness of 0.125 inch. And we are supposed to calculate the radial stresses, longitudinal and circumferential stresses in the walls of the cylinder when the tank is pressurized to 2000 psi. So first thing, we have already calculated, derived the formulas for the hoop stress. Let's say that formula was PD over 2T. So we have been given the outer diameter of the cylinder and the thickness. So what will be the inner diameter? For example, this is a cylinder. Yes.
Outer minus thickness.
So the inner diameter will be outer diameter minus thickness. So we have to subtract the thickness twice, from top and from bottom as well, right? So what will be the inner diameter? Just give me the answers quickly, because this is very simple and there is no complication.
11.75.
So the inner diameter is 11.75 inch. Now to calculate the, first let's calculate the radial stresses. So we derived yesterday that the radial stress is exactly opposite to the internal pressure. So the radial stress will be 200, or let's minus 200 psi. And what will be the hoop stress? The pressure is 200, the diameter is 11.75, and 2 times what is thickness? 0.125. So what is the hoop stress? Anyone?
So 9400.
It is 9400 psi. And similarly, the longitudinal stress, if you substitute all these values, you will get, or I can substitute only 9400. Let's just do the whole thing. 200 into 11.75 divided by 4 into thickness, 0.125. So what is the longitudinal stress? Is it 4900? Can someone confirm this answer?
4700.
How much is it?
4700.
4700. Okay, 4700 psi. Now, yesterday I told you one thing, that in the case of thin cylinders, the radial stresses are neglected. So now you know the reason why it is neglected. If you look at these stresses, this hoop stress is 9400 psi. This longitudinal stress is 4700 psi, but this radial stress is only 200 psi. So the impact of this radial stress is very small compared to these two stresses. So if a cylindrical section is designed considering these longitudinal and hoop stresses, it will automatically satisfy the condition of radial stress, and we don't have to take that into account. So that was the reason that these stresses are neglected in the case of thin cylinders. So, and in this type of in this topic or in the topics of cylinder, you are going to get the similar type of questions. There won't be much complexity, or if you know the use of this formula, you can solve any type of questions for the cylinders. So this is how you calculate the stresses in the cylinders. Now we are going to calculate the strains. Actually, these are small derivations, and I will explain them on the slides. Try to understand or follow me. If you have any confusion, just ask me at the spot. Or even if after you solve it, after conclusion of this lecture, you can ask me later if you have any question about this one. So the first strain that or the first deformation that we are going to study is the change in length. Now, if you see this figure, this longitudinal stress is causing the change in the length of the cylinder. So if we know we know that the strain is equal to change in length or any dimension. Let's say for this case, change in length over original length, right? So we know that the longitudinal strain is causing the change in length of this cylinder. So if we want to calculate the change in length of the cylinder, we will use this simple relationship. That is, change in length is equal to longitudinal strain multiplied by original length. Now we know the original length of the cylinder. If we can figure out what is longitudinal strain, we can calculate the change in length of the cylinder. Now we also know from the basic principle of mechanics that when the strain is being produced in one direction, let's suppose the longitudinal strain is epsilon L, but when the strain is being produced in one direction, it will produce or it will have a small impact on producing the strain in the other direction as well. So what is our other direction? One direction is the radial. What? I didn't hear you.
आप बहुत तेज बोल रहे हैं मुझे कुछ भी समझ नहीं आई
Okay, let's talk about this one again. So first thing that we are going to calculate, or we are going to develop the formulation was for the change in the length. Okay, so if you look at this figure over here of the longitudinal stress, from this figure you can see that this longitudinal stress is causing the change in the length of the cylinder. So if I want to calculate that how much change is being produced in the cylinder, I will use this simple formulation, that is, we know that strain is equal to change in length over original length. So which strain is causing the change in length? That is longitudinal strain, right? So any confusion up till this point?
No, sir.
So now I will just rearrange this equation, and I will get the change in length that is equal to longitudinal strain multiplied by original length. So what is longitudinal strain? We know that strain, let's suppose the longitudinal strain is epsilon L. Okay, but we know from the principle of physics that when the strain is being produced in one direction, it will also produce a minor strain in other mutually perpendicular direction. So in the case of cylinders, we have three direction or three type of stresses, that is radial stresses, longitudinal stresses, and hoop stresses. But radial stresses we know are very negligible in the case of thin cylinders, so it can be neglected. So we are left with the longitudinal stresses and the hoop stresses. So when the strain is being produced in the longitudinal direction, a small strain will also be produced in this direction or in the direction of hoop stresses. And how we relate it, we also know from the basic principle of mechanics that the strain produced in the other direction will be multiplied with the Poisson ratio into strain in the hoop direction, which is this formulation. So the strain in the longitudinal direction will produce a minor strain in the direction of hoop stresses, which is given by this factor, that is Poisson ratio into hoop strain. So we know if we simplify this relationship, that is stress is equal to or strain is equal to stress over E. We know this relationship as well. So if I substitute this relationship into this formula, I will get for epsilon L sigma L over E minus nu sigma H over E. So if I take 1 over E as common from this one, I am going to get sigma L minus nu into sigma H. So this is the formula for longitudinal strain. Now just I have to substitute this formulation into this equation over here, and I will get the change in length. That is 1 over E sigma L minus nu into sigma H multiply L is the original length. So what is sigma L? We have already derived the relationship for sigma L, that is PD over 40 minus nu. And what is sigma H? Sigma H is, again we have derived the relationship, that is PD over 2T multiply original length, that is this one. So when we are going to simplify this relationship, we will get this formulation for change in length. Now, if you know how much pressure is being exerted, the diameter of the cylinder, the thickness, the elastic modulus of the cylinder, the Poisson ratio, and the original length, you have to use this formulation to calculate the change in length. So is there any confusion about this one?
सर ये हुक स्ट्रेन के साथ म्यू क्यों आया?
With the hoop strain, because if you remember from very basic classes of mechanics, that when the stress is being produced or the strain is being produced in one direction, let's say in this cylinder there won't be only one strain, only one stress. There are stress in the three direction, that is in the radial direction, or if the radial stresses, the longitudinal stresses, and the hoop stress as well, right? So when the strain is being produced in one direction, let's say in the longitudinal direction, a small strain will also be produced in the mutually perpendicular direction. So the mutually perpendicular direction to this longitudinal stress is this hoop stress and this radial stress. So radial stresses we are going to neglect, but we have to consider this hoop stress. Now the amount of strain that is being produced in the other direction is this Poisson ratio into EH. There won't be full strain produced in the other direction, but only a small quantity. And this small quantity has been determined that it should be multiplied by the Poisson ratio factor to get, for example, Poisson ratio for a material is, let's say, 0.2. So let's say the strain produced in the opposite direction is somewhat 0.001. So when you multiply these two factors, you are going to get a small answer, let's say something of like this one. So the strain produced in the longitudinal direction will not be actually this value. It will be reduced by a factor mu into epsilon h. Have you got my point?
Yes sir, thank you.
The next thing is change in diameter. Now again, from this figure you can see that the longitudinal stress is causing the change in the length, but the uh, this hoop stresses, yes, this hoop stresses is causing the change in diameter because it is acting in the perpendicular direction, and when the stress is being produced in this perpendicular direction, it will either cause the cylinder, for example this is the cylindrical shape, and if there is a stress in the y direction, it will cause an increase or decrease in diameter. So this hoop stress is basically causing either the reduction or the increase in the diameter of this cylindrical element. So we have to, if we can calculate this hoop strain, we can calculate the change in diameter of this cylindrical element. So again, we have to apply the same principle to calculate or to formulate the formula for the calculation of diameter, change in diameter. Let's say the change in diameter is again the diametric strain multiplied by original diameter. So what is, which strain is causing the change in diameter? That is hoop strain. So again, the concept is same, that when the strain is being produced in one direction, it will be reduced by a certain factor because of the strain that is being produced in the mutually perpendicular direction. So now the actual strain is being produced in this direction, that is epsilon h, and the reduction will occur due to the strain that is being produced in the longitudinal direction. And how much reduction is being produced? It will be mu into epsilon L. And what is original diameter of cylinder? That is this factor D. So we have this diametric strain epsilon h minus nu epsilon L into D. Again, you substitute stress over strain relationship into this formula, and you substitute the values of hoof stresses and the longitudinal stresses. And when you are going to simplify this, you will get this formulation, that is PD over 4TE into 2 minus nu multiplied by D. So if you know all these factors, you can calculate the change in diameter of cylindrical element for a particular pressure and for a particular type of material. So is there any confusion about this one? So let's move on to the next one. The next thing is how can we calculate the change in internal volume of the cylinder. Now for the length and for diameter, we have the strain that we know longitudinal strain or longitudinal strain is causing the change in the length of the cylinder, and the hoof strain is causing the change in diameter of the cylinder. But we don't have any type of strain using which we can measure the change in the volume of the cylinder. So if we want to calculate the change in volume, and we have this formulation, that is strain is equal to change in the volume over original volume. In this equation, we have now two unknowns. We also don't know the change in the volume, and we also don't know the strain or the volumetric strain. So if we can figure out one of these factors, then we can use this equation to calculate the change in the volume. So in this formulation, we have to do a different thing. We know that the original volume of the cylinder is pi d square over 4 into L. So let's suppose we calculate or we derive the formula for this change in volume using the dimension of the cylinder. So can I write that change in volume is equal to final volume minus original volume? Okay, so in this equation, the change in volume is obviously final volume minus original volume. But in this equation, we know that the original volume is this one, that is pi d square over 4 into L. And the final volume we don't know, and we need to calculate this change in volume as well. So what will be the final volume of the cylinder? For example, if a stress is being applied, there will be a change in the volume of the cylinder. So what will be that volume? That will be final area of cross section. If this is the original area, so the final volume will be the final area of cross section multiplied by final length of the cross section. So let's solve this derivation onto whiteboard. Just give me a moment. Can you see the screen?
Yes,
Can
sir.
you hear? Okay. So now we need to calculate the change in volume. We know that the volumetric strain is equal to change in volume over original volume, right? So volumetric strain is epsilon V over delta V over this V. Now in the previous question, when we were doing, we knew what is hoop strain or what is the longitudinal strain, but we don't know what is volumetric strain. So we can't calculate the change in volume directly by using this volumetric strain. So either we have to figure out what is this factor, or we have to figure out what is this factor, or we have to represent it in the form of length or some known forces or some known factors, right? So we will do some small derivation. Actually, it involves simple steps. It won't be much complicated. So let's do it. So the change in volume or delta V will be equal to final volume minus original volume, right? So what is final volume? We know original volume is V, that is pi by 4 d square into L. And what is final volume? That we have to compute, and if we can calculate the final volume, we can calculate the change in volume directly. So let's suppose the final volume is final area of cross section into final length. So when there was no stresses applied on the cylindrical element, the diameter is, or the initial diameter is d, and the final diameter after the stresses have been applied is delta d, or the increase in diameter is delta d. And similarly, initial length is L, and the change in length or the final length after the forces or the stresses or strains have been applied is delta L. So if I want to calculate the final area of cross section, I would say that the final length of my section is pi by 4 d plus delta d whole square multiplied by L plus delta L, right? So any confusion up till this point? If there isn't any, we can move on. So we just need to simplify this formulation. That is pi by 4 d square plus delta d whole square. Now you just have to open this square root plus 2d delta d into L plus delta L. So if I simplify this one further, I will get pi by 4 d square into L plus delta d whole square into L plus 2LD delta D plus D square delta L plus delta D whole square into delta L plus 2D delta L delta D. So now this is the formulation for the final volume. But in this one, if you look at this formulation, that these factors, that is delta D, it would be a small factor. So when you are going to take the square of this factor will even reduce more. For example, if delta D is 0.001, and if you are going to take the square root of this factor, this factor will reduce even further. So we can neglect these quantities where there is a square root of delta function. For example, over here, there is also a square or product of these two delta. So it will again be a very small quantities. In this one also, there will be a square of these delta quantities. So we can neglect these factors and we will be left with final volume as pi by 4 d square L plus 2L d, that is this quantity, 2LD into delta D plus D square delta L. Okay. So this is the final volume that I can represent by FV. So now if I substitute this formula back into this equation of change in volume, this equation, I would name it as equation 1. So let's substitute it back into equation 1. Substituting final volume in equation 1. So you are going to get the change in volume as pi by 4 into d square L plus 2LD delta D plus d square delta L minus pi by 4 d square L. So if we simplify this one, what will happen? This factor, this whole factor will be cancelled with this one, and we will be left with pi by 4 2LD delta D plus pi by 4, or we can take it as common, plus d square delta L. So this is the change in volume. Now, if we know the length and diameter, and then we can calculate the change in volume. But again, in this equation, we have this factor delta D, which won't be given in the question. So if we can remove this factor as well, then it would be more convenient for us to calculate the change in volume of the cylinder. So let's try and do that also. So any confusion up till this point about how we got to this point?
सर आप कह रहे हैं डेल्टा डी हमें नहीं गिवन ना?
Yes, this won't be given to us because this delta D is obviously the stress or the change in diameter when the stresses have been applied. But in the question, for example, we would be provided with the stresses, not the changes in diameter or changes in length. So we should try to formulate this change in volume with respect to non-terms, just like we did in these formulation. For example, in these formulation, you see that all of these factors are not dependent on the stresses. These are the original factor of the original input parameters for the cylindrical element, right?
Yes, sir. तो डेल्टा एल भी हमें एलिमिनेट करना होगा इसमें?
Yeah, yes, we need to eliminate these factors. Or we need to come up with some formulation that we don't have to use these factors. So if I substitute this equation back into the equation of change in volume, that is this equation, I would name it as 2. So if I substitute the value of delta V into this one, what will I get? Epsilon V will be equal to delta V, that is pi by 4 2L D delta D. Hold on. Epsilon V is equal to pi by 4 2LD delta D plus pi d square over 4 into delta L. And what is original volume? This volume. This original volume is this one of the cylindrical element. So if I substitute this volume into this equation, that is pi by 4 d square into length. So what will happen if I simplify this one? Can I write it like pi by 4 2 LD delta D over pi by 4 d square into L plus pi d square over 4 into delta L divided by pi by 4 d square into L. Now this will be cancelled out. This whole factor will also be cancelled out, and we will be left with this length factor will also be cancelled out. This diameter will be cancelled with this one. So we will be left with 2 times delta D over D plus delta L over L. So what are these factors? What is delta L over L? Can anyone tell me this?
Change in
Strain.
length and change in diameter.
Which strain?
Longitudinal.
And what is this one? Delta D over D.
For lateral.
Yeah, hoop strain. So this is the hoop strain, and this is the longitudinal strain. Now we know the formulation of this hoop strain and longitudinal strain. From these slides, if you see, now this formula is for the hoop longitudinal strain, and this one over here is the formulation, or is the from this one we can calculate the formulation for the longitudinal strain. Let me show you how. We have derived this factor over here, that is delta D over delta D is equal to PD over 4TE 2 minus nu into D, and delta L is equal to PD over 4TE into 1 minus 2 nu into L, right? From these two figures. Now if you simplify this one, what is delta D over D? This D will go onto that side, so we will have delta D over D is equal to PD over 4TE into 2 minus nu, and delta L over L is equal to PD over 4TE into 1 minus 2 nu, right? So this delta D over D is again the hoop strain, and this delta L over L is the longitudinal strain. So I will substitute these value into this equation of epsilon V, and I am going to get 2 into PD over 4TE into PD over 4TE 2 minus nu plus PD over 4TE into 1 minus 2 nu, right? So if I simplify this equation, I will get epsilon V as PD over 4TE into 5 minus 4 nu or let me just do it. So this 2 will be multiplied inside, and I will take this PD over 4TE as common. This PD over 4TE as common, and I will be left with 4 minus nu, 4 minus 2 nu, and from here I will have plus 1 minus 2 nu. So this epsilon v will be Pd over 4 Te into 5 minus 4 nu. Okay. So now I know that what is the volumetric strain. So I have been given the question with all the factors and I've been asked to calculate the change in volume. How will I proceed? I know that change in volume or volumetric strain is change in volume over original volume. I can calculate the volumetric strain from this formulation and I can calculate the original value of the volume as that is pi by 4 d square into L and volumetric strain from this one, because from this all are the input parameters that are provided, that is pressure or the internal diameter, the thickness, the modulus of elasticity and Poisson ratio, and I can directly compute the change in volume. So the formulation for change in volume will be Pd over 4Te 5 minus 4 nu into volume. So any confusion about this derivation? Or any question about this one? So if there isn't any, we can solve one example just to see how these things work. So there is a cylindrical shell 1 meter in internal diameter and 3 meter long, and it has a wall thickness of 12 millimeter. If the shell is subjected to internal pressure of 1.2 megapascal, we are supposed to determine the longitudinal stresses, hoop stresses, change in diameter, change in length, and change in volume. We have been given the modulus of elasticity as 200 gigapascal and Poisson ratio as 0.3. So let's solve it. I have been given with the pressure as 1.2 megapascal, the internal diameter as 1 meter or equal to 1000 millimeter, and the thickness as 12 millimeter. E is given as 200 gigapascal and the nu was given as 0.3. And we are supposed to calculate the hoop stresses, longitudinal stresses, change in length, and change in volume, change in diameter. So what will be the hoop stress for this case? Again, we have to use the same formula, that is Pd over 2T. So the pressure is given as 1.2 megapascal. So that is 1.2. The internal diameter is 1000 millimeter. The thickness is 12 millimeter. So what is the hoop stress?
$50.
And what will be the unit of this one?
Megapascal.
Yes. What will be the longitudinal stress? Just keep on calculating and give me the answer. You just have to use the formulation.
100 megapascal.
100?
So either divide by 2 or multiply by 2. I don't remember.
25.
25.
25 megapascal. Yes. And the next thing is we need to calculate the change in length. So we just derive one formula for the change in length, that is Pd over 4Te into 1 minus 2 nu into length. So what is the original length that is given in the question as, let's look at it. So the original length is 3 meter, right? So the length is given as 3 meter, nu is 0.3. So the change in length will be 1.2 into internal diameter is 1000, 4 times thickness is 12, E is 200 into, or I can write it as 200,000 just to convert it into megapascal. And 1 minus 2 into 0.3, and the length is given as 3000 millimeter. This change in length. Can anyone give me this answer?
Sir, 1.5 into 10 to the power minus 4.
1.5 into 10 minus 4. Can anyone else check this answer? 1.5 into 10 minus 4. Are you using your calculators, or just one or two students are doing it, I guess?
Yes, sir. Yeah. 150 micropass.
1.5 into 10 minus 4. Hold on.
सर मीटर होगा.
It should be millimeter. Let me just confirm this answer.
Sir, meters.
If you use this equation, isn't the answer is 0.15? How are you getting 1.5? I just recalculated.
Yeah, 0.15.
Yes, it should be 0.15 millimeters. Because this E is given in the units of gigapascal, and we have to convert it into megapascal just to be consistent.
Sir, I was answering in meters. मैं meters में बताई थी 1.5 into 10 to the power minus 4.
Oh, okay, that's fine. So in millimeters, the answer is 0.15 by using all these factors. So let's calculate the change in diameter. So P is again 1.2. Original diameter is 1000. 4 into 12 into 200,000. 2 minus 0.3 multiply by, again the diameter is 1000. So what is the change in diameter?
Millimeter.
212.5 millimeter. So this is the change in diameter due to the internal pressure of 1.2 megapascal. So the last thing is we need to calculate the change in volume. So we just derive one relationship over here, and we will use the same relationship to calculate the change in volume. So I've written it over here. So just substitute the values. Pressure is 1.2. The original diameter is 1000. 4 times thickness multiplied by E, that is 200. 1005 minus 4 into 0.3 multiplied by pi by 4. Diameter is 1000 whole square and the length is 3. So the change in volume is what? 1.11. Can you give me this answer?
1.119 exponent 6.
1.119 into 10 raised to power minus 6.
Positive 6. Positive 6 आया.
Okay, yeah, it's in millimeter cube. Can someone else confirm this answer as well? Yeah.
Yes, sir.
So this is a change in volume. Now in this question you were asked that the cylinder is under a pressure and you now know how to calculate the changes in the stresses in different direction, that is longitudinal, hoop stresses, diameter or change in diameter, length or volume. So this is all about the thin cylinder and I would ask you to again go through these derivation and you can ask me particularly in these one because we haven't solved this on the board. If there is any confusions you can ask me right now or you can also send me a message later. So this is all about the thin cylinders and from the next lecture we are going to start the topic of thick cylinders. So if you have any question now you can ask me. If there isn't any then
Sir,
yes.
is Poisson ratio equal to is it also equal to the hoop strain over the longitudinal strain?
What? Poisson
Sir,
ratio?
yeah.
Yes, it is the same Poisson ratio.
Okay.
Actually, the purpose of Poisson ratio is that it can cause the reduction in stress. For example, in the strain. Hold on. Let me just explain briefly. So when there is any material and there is a strain, this is a 2D material. So let's suppose there is any material on which a strain is applied in one direction. So due to that, firstly we need to apply the force. Due to that force, the stress is produced, and due to that stress, the strain is being produced, right? So when the stress is being applied or the force is being applied in one direction, there will be small stresses that will be produced in other direction as well. So originally, let's say in the longitudinal direction, the strain produces this one, but the total strain in the longitudinal direction will not be this one. It will be reduced by a certain factors due to the strain being produced in the other direction. Now that factor is related with this one by this Poisson ratio, and we have to multiply the strain in other directions with this Poisson ratio factor, and this is the net strain or the total strain which is being produced in any direction. It won't be directly this one. It will be reduced by a small factor, which is this factor over here. So it's not a very complex concept. Any other question?
Sir, this strain is produced in longitudinal direction, net and strain.
If we are doing for the change in length, then yes, this is the longitudinal strain. And if we are doing, for example, I would say that a longitudinal strain is epsilon L. But again, due to the concept that it produces the strain in other direction as well, so it won't be directly epsilon L. It will be slightly less than epsilon L. So if we are doing for the circumferential, that will be circumferential hoop strain minus nu, because in this case the stress is being applied in the direction of hoop stress, so the strain will be produced in other direction as well, so that is nu into epsilon n. So this is the hoop strain. So this is actual value, and due to reduction this is the net value in the hoop direction. Any other question? So if there isn't any questions, this is it from our class, and we will meet tomorrow for structures lecture. Thank you very much.